In the second module, we will continue on along the different calorimetric techniques. So let's start from the homogeneous calorimeter. So we said that homogeneous calorimeters are those where there is only one kind of medium, which will play two roles: the role of the absorber and the role of the sensitive medium where a signal will be created, which will then be translated into the energy. So the one way of building homogeneous calorimeters is with using crystals, where the light emission is related to the structure of crystals themselves, and so the incident charged particles will create electron-hole pairs, and photons are emitted when electrons return to the valence band. So the electron or the photon is completely absorbed, and the produced amount of light is measured by photomultipliers, or it is measured by solid state photon detectors, so it's silicon photomultipliers. So it's anyway a device which will measure the photons, and the good point is that the crystals they are transparent, and so they let the light to pass through the medium itself until they reach these photomultipliers. So there are different types of crystals made of sodium iodine or cesium iodine or BGA, so there are different kinds, and you see the typical parameters here listed in terms of Morier radius or radiation length, the density, all these relevant parameters which are important for the computation of the shower development. And different calorimeters have been built with these techniques. For instance, there's this lead-based calorimeter for the CMS experiment at the LHC. And indeed, the good point of calorimeters is that they can be very fast. The signal generation can be very fast, and sometimes they are also used to trigger on some specific process. So this is how crystals are used for developing homogeneous calorimeters. So this is a drawing of one of these calorimeters. And one can also make calorimeters, homogeneous calorimeters with noble liquids. So this could be liquid argon, for instance. And so when the typical charged particle traverse these noble liquids, roughly half of the energy is lost by the ionization process, and the other half into scintillation. So scintillation will create directly photons, and the ionization will create electron-ion pairs. And so if you can collect both signals, the charge of the electron-ion pairs and the light of the scintillation light, this of course will provide the best energy resolution. And so it is not easy to extract both the light and charge in the same instrument, but in principle it is possible. So the krypton is also sometimes preferred in homogeneous detectors due to the smaller radiation length, so which makes, of course, the calorimeter more compact. While liquid argon is frequently used because it's cheaper and because of its high purity in the sampling calorimeters, so it's more used for sampling calorimeters. So but anyway, so if you take just to give you the typical signals that you have, well, you have for instance in the liquid argon, if you have a field of 1 kilowatt per kilovolt per centimeter, then you have a drifting speed of about 5 millimeter per microseconds. So if you have a 5 millimeter gap, this will mean that it takes 1 microsecond for all electrons to reach the electrode. So the speed of the ions is much slower, from 1,000 to 100,000 times slower, and so they do not actually contribute to the signal because of course you have a limited integration time. So there are other kinds of homogeneous calorimeters, like the one built for the NA48 experiment at CERN, and so this gives you the typical energy resolution. So you see that these calorimeters, they get an energy resolution which is better than 1% already at around 20 GeV. And so this is for this that's a very good excellent resolution. Then, I mean, if we analyze the different contribution to the relative energy resolution, we have the stochastic terms, which goes proportional to 1 over the square root of E, and so we said that already. This comes from the Poissonian fluctuation in the number of particles in the shower development, and this is normally the leading term. Then there are also additional terms. There is the noise, the so-called noise terms, which comes from all the noise of the electronics and all the readout chain. So if you assume that this noise does not actually depend on the energy, then you have that when you do the relative energy resolution, this is a factor which goes proportional to 1 over the energy itself. And then you have another term which is an instrumental effect, which is, for instance, related to the fact that the response of a calorimeter depends on the point where your energy is released. So if, for instance, you may have some dependence on the impact point, and then you have a constant term due to that. And so this shows you, for instance, on the right, I mean, for the NA48 experiment at CERN, that you have the different typical constant, the typical A, B, and C values. I mean, for this, for the different contributions, which normally they add to each other in squares. But normally, I mean, the second term, the one due to the electronics, is less important than the other two. Then sampling calorimeters, in general, they have an energy resolution which is worse than homogeneous calorimeter because, of course, of the sampling fluctuation. Because a large fraction of the energy is released actually in the passive material. So then the resolution is typically in the range of 5 to 20% over the square root of E. But of course the advantage is that they are very, very compact, and so they can also be segmented longitudinally and laterally, and so they can provide a better spatial resolution, and also a better particle identification compared to homogeneous calorimeter. So the active medium can be scintillators, they can be solid state detectors, can be emulsion films, can be gas detectors. So, and the sampling fraction is defined as the energy deposited in the active material divided by the energy deposited in the passive material. So one can also make this sampling calorimeter with gas, which were commonly used, for instance, at lab because of their low cost. And but then since the energy gets to the energy resolution is relatively modest. I mean, when it is extremely important to have very accurate energy measurements, then this is, of course, they are less competitive. So one can use solid state detectors as active medium with using silicon, and the advantage is that there is a very high signal to noise ratio because the signals are pretty large because of the large dynamic range, and they are often used on a small scale also as device monitoring the luminosity. The disadvantage is the high cost, preventing very large calorimeter, and also the modest resistance to the radiation. I mean, the radiation hardness of this device. So then one can make sampling calorimeters with scintillators. A large number of sampling calorimeters, they use actually organic scintillators arranged either in plates or in fibers. And the drawbacks is that the optical readout suffers from the radiation damage and from non-uniformities at various stages, and they are often the source of a large constant term. So the CLOE electromagnetic calorimeters, they have reached 5% over the square root of E by using this kind of technology. Then one can use liquid detectors, noble liquid, for instance at cryogenic temperatures. But typically, if they are at the liquids, if they are at room temperatures, they have a poor resistance to poor radiation hardness, say, and they suffer from purity problems. So when using noble liquids, they tend to be at cryogenic temperatures. So they can be operated in ion chamber mode, the deposited charge in this case is large and it doesn't need multiplication, which provides a better uniformity compared to gas calorimeter, where you have large amplification of the with an avalanche process. And so they are relatively uniform, easy to calibrate, because the active medium is homogeneously distributed inside the volume, and provide good energy resolution. For instance, in Atlas this is about 10% over the square root of E. And they are radiation hard. With the standard liquid argon sampling calorimeters, the alternating absorber and active layer, they are placed perpendicular to the incoming particles. So then of course one needs relatively long cables, which can cause a signal degradation with some dead space between the calorimeters towers, and also reduce the hermeticity of the overall apparatus. For the Atlas liquid argon calorimeter, I mean, this was solved. This problem was solved by placing the absorber in a peculiar geometry, which is parallel to the particle directions, and so at the end they have provided very good energy resolution with this different three terms, so that the leading term is 10% over the square root of E, and then there is this terms due to the electronics, which is 0.25 over the energy, and the 0.3% is this constant term. One can actually make sampling calorimeter by alternating lead or tungsten to the emulsion films. So we have described in a previous lecture what an emulsion cloud chamber is, and indeed this is the case. This is a typical opera brick where the total thickness is 10 radiation length. Of course, I mean, if you want a good containment of the shower, then you have to double roughly this length. But even with such a short radiation length, so this was not really a calorimeter. It was not really meant to contain all the shower, but just to identify the electron at the beginning of the shower, and to start seeing the development of the shower. So this was performing extremely well in disentangling electron and pi zero. So the electron and pi zero separation is a very important issue in neutrino physics, because then you may misidentify neutral current interaction as electron-neutrino interactions, charge current, electron-neutrino interaction. So that's a key point, and indeed there is this device has a very high sampling frequency, because there are about six active layers every radiation length. So the sampling frequency is extremely high, and they have extremely high spatial resolution. This turns into a very high purity of the electron pi zero separation, because then you see the electron, you identify the electron because you see the charged particles initiating the shower, while you, on the other side, for the photons, you will see a neutral particle initiated in the shower, because you are capable of observing this gap between the start of the shower and the origin of the photon, which is highlighted by the neutrino vertex. And so this is the typical electron neutrino interaction with a pi zero in the final state. So you see that there is a primary electron. This is in the transverse plane on the left. The primary left electron is highlighted in green, and then you have the two photons in blue and red, and you see this how it is. It shows up in the side view on the right. Then the typical algorithms for the shower and energy reconstruction, they are based on counting how many electron and photon and then positrons are found in a certain cone with a given opening angle. So for the you have different variables which can be used to discard instrumental background due to the fact that inside the cone you may have other particles which are not related to your shower development, and this is because emulsion, they do not have the timing information, so they do integrate over time. So you can define the opening angle of your cone. You can define you can use as a parameter the impact parameter of your track to the initial point of the shower. Then you can use also the angular difference between your track segment and the original incoming electron, direction of the electron, which is coinciding with the axis of your cone. And then you can also, in case you use also subsegments, then you can have a kind of chi-square which gives you the quality of these track subsegments. Then you have different performances in your depending on the origin of your neutrino interaction. This is very much different if you when you have neutrinos, because their interaction will not be, I mean, if you have an incoming electron, then of course the shower origin will always be at the entrance. But for a neutrino, if the electrons originates in a neutrino interaction, then your neutrino will interact uniformly in your detector, and so you will have some of the electrons originated in the very upstream part, and the same fraction originated in the very downstream part. And then of course the containment of the shower is very much different in the two cases. So we divide the emulsion cloud chamber in different zones, and then we analyze, for instance, the performances of the electrons when they are originated in the first part of the brick, and then here you have the different variables how they look like, and then you at the end you do a calibration function of your of the number of particles versus the energy, the true energy of your event. Then you reconstruct the energy with a resolution of about 21%, and you with your neural network approach, you end up with a number of segments, track segments in your events which belong to the signal, which is 160, and a contamination of say background tracks which is about 10%. Then if you extend the analysis also to the downstream emulsion cloud chamber, then you of course have a much larger thickness, and then you can also start analyzing the events in the downstream part of your brick. And if you do the similar analysis, then you end up with a resolution which is not very much different from the previous one, although there are larger tails due to the containment of the event, and to the cross-link to some energy which is lost in the material, which is in between the two bricks. And I leave you here with some questions just to test that you have got the main messages of this module.